Okay, looking at the calculator multiple choice questions here, and remember these are calculator active problems, so don't hurt yourself doing things by hand if you could save yourself some agony on the calculator. Alright, so number 21 is a little bit wordy, and if you're not good at science, the units will help you out, but it talks about the density of a rod, and it tells you this is the function for density, then it gives you a unit. If you look at that unit, that is a rate, grams per meter, and then they ask you the mass in actual grams. Well, if I want to go from a rate to an amount, you will do the antiderivative. So that's going to be the antiderivative of the density function, the rate function. And they tell you that the rod is 1 meter long. So I'm going to measure the density over the length of the rod, and that would end up giving you your that'll end up giving you your mass. I know the answer is 1.333 because I've already punched this in the calculator, and I know that that's the answer. You would simply plug that in the calculator, and there we go for 21. 22, a little bit misleading because it gives you a graph and it asks for the area of the shaded region, and I'm pretty sure the vast majority of you are thinking, oh, that's an easy one. That's the area from A to B under the function f of x. The problem is when they ask about a shaded region, like they're looking specifically at the region, they're not saying specifically what is the area under the curve. The area of a shaded region is going to be measured with a positive number. Well, this area given by that antiderivative would actually be negative. So in order to get the positive value of that, I'm simply going to multiply both sides by -1. And if I multiply by -1, that will give me the negative antiderivative from A to B, f of x dx. And when you multiply by negative, you flip the sign, and that turns it positive. Negative area A to B is not given, but notice B is area from B to A. That is the same thing. If you want to get rid of that negative, you can flip the limits of integration and change the sign out front, and that actually would give you the positive area that represents the area of the shaded region. Okay, 23 is going to be the most difficult and the most vague problem we have. It's a good thing this is multiple choice because that kind of gives you some options. It is an improper integral, so we always change improper integrals to limit. So we'll do the limit as k approaches infinity of the antiderivative from 1 to k of 1 over x to the p. That's what we're doing. Well, not x minus p, 1 over x to the p. There are 3 key options that I'm going to focus on for this integral. And I know that if p is equal to 1, this turns into a very nice integral because it would be the antiderivative from 1 to k of 1 over x dx, and that antiderivative is simply the natural log of x from 1 to k, which would be the natural log of k minus natural log of 1. And if you do the infinite limit of that, as k approaches infinity, this thing becomes the natural log of infinity minus 0, and that diverges. Now that is going to help us eliminate a lot of options. We do know that the integral does not converge for all values of p because I just showed that at 1 this will diverge, so it's not that one. At 1 it diverges, so it's not c. Also, 1 is greater than 0, and a is suggesting that this integral will converge for all positive p's. Well, that's not true because at 1 it will diverge, so we've eliminated a. My other 2 options are p is greater than 1 and the integral always diverges. So now what I'm going to do is I'm going to see what happens if p is greater than 1, and this is where it gets very tricky because unlike that first option where the p just turned into 1, this one we're going to have to keep a p into the problem, So that's going to be the antiderivative of from 1 to k of 1 over x to the p. If p is anything but 1, I'm going to have some funky exponent down here. I'm going to pull this up to the top and make it x to the negative p, and I'll integrate it that way. The only time I'll leave it in the denominator is if it's a natural log, and I've already worked that solution. So this antiderivative would be x to the negative p plus 1 divided by negative p plus 1. Not a real fan of the way that's written. I'm just going to change that to x to the 1 minus p over 1 minus p. Now I'm thinking if p is greater than 1, if p is greater than 1, then 1 minus p is going to be negative. If p is greater than 1, then 1 minus p is negative. And that means I'm going to have something along the lines of x to the some negative number. We'll say negative 4. Well, if I have x to negative 4, I generally think of that as 1 over x to the 4th. So I'm going to do the same thing here. I'm going to take that x to a negative exponent and move it to the bottom. So the 1 minus p is going to stay down there. But I'm going to take that x and move it to the bottom, and you move it to the bottom by changing the sign. So if it was x to the 1 minus p on top, it's going to become x to the p minus 1 on bottom. And all I did is I just took the negative of that. You could also say negative 1 plus p. Now remember, we are evaluating this from 1 to k. 1 to k. And when I plug in 1 and k, I now have 1 over 1 minus p times k to the p minus 1 minus 1 over 1 minus p times 1 to the p minus 1. Now I want to look at this and see what happens as my k approaches infinity. So again, we're going to evaluate our limit right here. And if k is approaching infinity and p is bigger than 1, now I have 1 over 1 minus p, which is a constant, times infinity to the p minus 1. But if p is positive, then that's going to be infinity to a positive power. Minus 1 over, and now this is not going to be affected. 1 minus p to the, and 1 to the p minus 1. Again, if p is a positive number, that's just going to end up being 1. 1 to any exponent is going to be 1 when we're dealing with real numbers. And 1 over infinity is 0. So 1 divided by infinity is 0 minus 1 over 1 minus p. So I ended up getting, even though it's in terms of p, I actually did get an answer that was not infinity. So therefore, if p is greater than 1, this thing ends up converging. And I warned you ahead of time that this is going to be kind of a confusing mathy type problem. But that, if you have anything like this, that's called a p function, 1 over x to the p. It will always converge if the exponent on p is something larger than 1. Whew. All right. 24. I'm going to play with a few properties of integrals here. I'm going to change this integral right here to the negative integral of 1,000 to a of 8 to the x dx, and I'm not going to change the rest of the problem. Now the reason I'm doing this, and I'm actually subtracting that, the reason I'm doing that is because I now have created a minus and minus. That's actually going to end up being plus the area from 0 to 1,000 of a function plus the area from 1,000 to a of the same function is going to end up being the area from 0 to a of that function. And the reason I did that is because when I see multiple integrals that you're adding and subtracting, I see similar limits of integration, and I see an exact definite integral, then I'm going to steer towards that property of logs, property of definite integrals, which says the area from a to b of f of x plus the area of b to c of the same function is the area from a to c of that function. So that's the property I'm playing with. And I kind of identified at the beginning that this was very similar to that property. So what I know is that the area from 0 to a of 8 to x dx ends up equaling 10.4, and now it's just a definite integral. I'm going to find the antiderivative of 8 to the x, which is 8 to the x divided by the natural log of 8. I'll evaluate that from 0 to a. This is supposed to equal 10.4. That would be 8 to the a over natural log of 8 minus 8 to the 0, which is 1, over natural log 8 equals 10.4. And this is a calculator problem, So what I would do on this one is I would actually move the 10.4 over, make it 8 to the 8 over natural log 8, minus 1 over natural log 8, minus 10.4, set that equal to 0. I would graph and find the roots. And when you do that, it turns out that the answer is 1.5. Let's see, 25. Looks like playing with more properties of integrals. This time we don't have a true function. I mean, we do, but we don't have a defined function. We don't have anything that I could actually do the antiderivative of. So I'm a big fan of graphs. I don't know if I've ever mentioned that to you before, but I'm going to graph this. I don't know what my function f of x looks like. I'm just going to have some kind of a visual to help me along here. What I do know is that the area from 0 to 3, that area right there, this area from 0 to 3, the yellow area is an area of 6. Right? Then you're told that the area from 0 to 4, I'm sorry, 0 to 2, so the area up to 2 is 4. So now I'm kind of confusing myself. So that's for the whole area. Let me see if I can move that 6 somewhere. The area from 0 to 3 is 6. Where's my yellow highlighter? There it is. That's not yellow. There it is. So the area from 0 to 3 is 6. Area from 0 to 2 is 4. And I'm not even reading the rest of the question. I know that, therefore, this must be an area of 2 to complete the 6. Then the problem is actually asking what is the area from 3 to 2. Well, the area from 3 to 2 of f of x dx. Well, I already know the area is 2 above it, but that's from 2 to 3. 3 to 2 would actually be negative 2. So I would actually just graph that out and think about where the areas are and subtract them. Let's see, looks very similar. Looks very similar. We are again given an unknown function, and the area from 1 to 4 is 7. Then we're given this thing. What I'll do on this one is I'll split this up as much as I can. That's the antiderivative from 1 to 4 of 2 f of x dx plus the antiderivative 1 to 4 of 5 dx. This one, I could pull the 2 out. Antiderivative 1 to 4 of f of x dx. And that was given to us. Area from 1 to 4 of f of x is 7. Right? Then there's a 2 out in front of that. Then plus, and this one I could actually integrate. So plus the antiderivative of 5 is 5x. Evaluate that from 1 to 4. So that's going to be plus, plug in 4, 5 times 4 is 20, minus, plug in 1, 5 times 1 is 5. And so I ultimately end up with 14 plus 20 minus 5 is 15, which is 29. Notice that even though these are on the calculator portion, a lot of them can be done without a calculator. Don't feel like you have to use your calculator simply because it's in your hands. Okay, this one's probably my favorite kind of question. We're given the rate of change, f prime, an initial condition, and they want to know f of 3. F of 3 is going to be f of 1 plus the area from 1 to 3 under the rate of change function, the root of 1 plus x cubed. And that one we'll throw in the calculator. I haven't done this one, so I'm going to plug that one in. That was, what was it? F of 1, which is 5, plus antiderivative from 1 to 3 of the square root of, was it 1 plus x cubed? Yeah. 1 plus x cubed dx. I'm going to hit Control Enter to force a decimal answer, and you get 11.2299. 11.2299, which would be E. One of the most common mistakes people will make on these is they'll forget to add the f of 1. F of 1 was 5. And notice that if you did not add that 5, they do have the option for that very common mistake. let's see, there's g of x. We need to compute g prime of 3. Before you find any value of a derivative, you must first actually find the derivative. So if that's g prime, this is one of those lovely fundamental theorem of calculus questions. You plug the 2x in for the t, and you multiply by the derivative of what you plugged in. So g prime of x is that. I need to compute g prime of 3. So g prime of 3 is going to be f of 2 times 3 is 6 times 2. That would be f of 6 is 7 times 2 is 14. See, 29, midpoint Riemann sums with 4 subintervals. Okay, so I'm going to go from 1 to 9. So 2, 3, 4, 5, 6, 7, 8, 9. I just like to organize my thoughts this way. And my rectangles have a base of 2 because I have 4 subintervals. Right? Just a visual here. Right? And you can find your delta x by doing the b minus a over the number of subintervals. That gives me 2. And we're using midpoints, so my height is actually going to be determined by the function's values at 2, 4, 6, and 8. So my setup is going to be my base, which is 2, times my height at 2, which will be f of 2, my height at 4, my height at 6, and my height at 8. And this is a fairly nice function, f of 2, because the function is just x squared. That's 4 plus 16 plus 36 plus 64. And let's see, should I do that in my head? Should I do that without a calculator? That's what, 20 plus 36 is 56 plus 64 is 120. And 2 times 120 is 240, which is option C. See, number 30. Table above, another Riemann sum. Compute the left-hand Riemann sum from 1 to 3 using 4 subintervals. So I'm going to go from 1 to 3 with 4 subintervals. Pay attention to this one because my bases are not the same. My first base is 0.75, my second base is 0.25, my third base is 0.5, and my fourth change is 0.5. That means we can't use a standard formula where you factor out the bases like I did on number 29. So if I'm going to do Riemann sums here, I've actually got to treat it as 4 independent rectangles. And I am using the left-hand side as the height. So my first rectangle will have a height or a base of 0.75. And the height of my first rectangle is going to be my function's value, f of x. So we're actually not going to use f prime. It's the function's value on the left-hand side, which is 4. So 0.75 times 4 plus 0.25. And the left-hand side of that interval has a height of 12. 0.5, the left-hand side of that interval is a height of 6. 0.5, left-hand side, height of 12. 3/4 of 4 is 3. 1/4 of 12 is 3. Half of 6 is 3. And half of 12 is 6. So 9 plus 6 is 15. B. And number the last. Table above to compute that area. Same table as the previous problem, only a different question. Well, with any area, it'd be nice if you could find the antiderivative, and this one actually sets up very nicely because the antiderivative of f prime would just be f, and we're evaluating that from 1 to 3, which is simply going to be f of 3 minus f of 1. F of 3, again, we're not going to use the f prime row. F of 3 is 2 minus f of 1 is 4. And we get negative 2. There we go.